three-phase half-wave rectifier with a resistive load. So here is our diagram for the three-phase half-wave rectifier with a resistive load. This is our resistive load here. So when we talk of three-phase half-wave, we have three phases and we have a rectifying device in each phase, so whereby we have one diode per phase. So if you look at our diagram, you can see the primary of our transformer here is in delta, while the secondary, the transformer is in star, whereby we have a fourth wire here, which is the neutral. So, and here we have our output waveform. Now, for the circuit operation here, so each and every diode will conduct at a particular time. So when voltage V1, when V1 is more positive than V2 and V3, then our diode D1 will be conducting, that is between 0 up to pi over 6, between from pi over 6 to 5 pi over 6. So at 5 pi over 6, it will cease to conduct. Then again, voltage when V2 is more positive than V1 and V3, diode D2 will conduct, that is between 5 pi over 6 and 9 pi over 6. The same applies to when V3 is more positive than V1 and V2, the diode D3 will conduct, that is between 9 pi over 6 and 13 pi over 6. So that is how the conduction takes place. And our secondary winding voltages, V1, V2, and V3, they are normally displaced at an angle of 120 degrees. So this is how the output waveform appears. So you can see it is better compared to the single phase. And these are our secondary voltages. I've used different colors so that you're able to see them properly. So now, when I go to the analysis, we want to see how we are getting these limits here. That's the main area. So how are we getting the limits? So now we can see at point A, there are some two voltages that are common at that point. That is V1 and V3. So at point A, V1 is equals to V3. And as we know that these voltages, they are normally 120 degrees apart. So you can say, but V1 is Vm sine omega t, and V2 will be Vm sine omega t minus 120 degrees, while V3 will be Vm sine omega t minus 240 degrees. So if we are saying that at point A, V1 is equal to V2, so we can equate the two. So therefore, it implies that Vm sine omega t is equals to Vm sine omega t minus 240. So we can expand this using the compound angle formula. So we say that Vm sine omega t. So maybe I can use a subscript A to show that it is at point A. Omega t at point A. Omega t at point A. So Vm sine omega t at point A will be equals to Vm. So if I expand this, I will have sine omega t at point A cos 240 minus sine, minus cos omega t at A sine 240. That's what we have after the expansion. So you can see Vm can cancel, so that we have sine omega t at A is equals to sine omega t at A cos 240 minus cos omega t at A sine 240. So I can have my omega t at A is the sine. So omega t's. So we shall have sine omega t at point A into 1 minus cos 240 equals to negative cos omega t at point A sine 240. So divide both sides by sine, shall get tan, so shall have sine omega t at A over cos omega t at A will give us minus sine 240 all over 1 minus cos 240 So if you simplify this, you will get root 3, that is sine of 240. So it will be root 3 all over 2 all over 3 over 2. That is root 3 over 3. So that is the tan, because sine over cos is tan. So this equals to 0.577. So the angle, which is omega t at point A here, will be 30 degrees, which is equivalent to pi over 6. That is the tan inverse of 0.577. It gives us pi over 6, which we have here. Then you can also consider point B. You can see at point B now V1 equals to V2. So you can say at point B, V1 equals to V2. So we have the two voltages. So that is V1 is Vm sine omega t at B. Vm sine omega t at point B is equals to Vm sine omega t at point B minus 240. So we undertake the same procedure. So we shall have, so Vm and Vm goes. So we have sine omega t at point B to be equals to sine omega t at point B cos 240. Okay, just a minute. This should be 120. V2 is 120, not 240. 120. 120. Yeah, our V2 was 120. So if we expand this will be minus sine 120 cos omega t at point B. So this will also give us again sine omega t at point B divided by cos omega t at point B will be equals to minus sine 120 degrees all over 1 minus cos 120. So if we simplify this, we shall get the angle, that is the tan inverse. So omega t at point B, it will be 150 degrees. That is the tan inverse. 150 degrees, which is 5 pi over 6. 5 pi over 6. So now we want to do the analysis. The reason why I was doing this was to know my limits when getting the VDC and the VRMS. So my limits are between pi over 6 and 5 pi over 6, which I had shown here before. So I want to go to analysis now. So VDC, so we have 3 phases, so 3 all over 2 pi, that is the period. So we integrate from pi over 6 to 5 pi all over 6, that is Vm sine omega t with respect to omega t, which gives us 3Vm all over 2 pi into negative cos omega t. Limits are from pi over 6 to 5 pi over 6. So simplifying this, it will give us 3Vm (3 into root 3), 3 into root 3 Vm all over 2 pi. That one gives us the VDC, which we can have as 0.827 Vm. So that is our VDC. So we can also get the IDC, root mean square current, IDC, which will be VDC divided by our load resistance. So you can have a 0.827 Vm all over RL. So you can simplify as 0.827 Vm divided by RL, you can get Im. Then VRMS will be the square root. So we have 3 all over 2 pi, the integral, from pi over 6 to 5 pi over 6 Vm squared sine omega t with respect to omega t. So this gives 3 Vm squared all over 2 pi the integral from pi over 6 to 5 pi all over 6 1 minus cos 2 omega t all over 2 d omega t. So we get a square root here. So simplifying this, we shall have 3 Vm squared all over 4 pi into omega t minus sine 2 omega t all over 2. So pi over 6 to 5 pi over 6. Then we need to get the square root, which you can raise to a half. So simplifying these, we get 0 point, because we shall have Vm into a half plus 3 root 3 all over 8 pi into a half, giving us 0.841 Vm. That will be the VRMS. VRMS. We can also get the IRMS. IRMS be VRMS all over RL. 0.841 Vm all over RL. 0.841 IM. That is our VRMS. You can also get the ripple factor. Ripple factor which is the square root VRMS squared all over VDC squared minus 1. So if we substitute 0.841 all over 0.827 squared minus 1, then we get the square root. That's why we are raising to a half. Gives us 18.47. 18.47%. So we can also get the efficiency, the rectifier efficiency. PDC see. VDC times IDC will give you PDC, and VRMS times IRMS. So this will be 0.827, because we have the expression for VDC, IDC, VRMS, IRMS. So it will give us that squared all over 0.841 squared times 100. It will give you 96.7%. So you can see how the efficiency is better compared to single phase, meaning as the number of phases increases, the better the efficiency of the rectifier. So for the peak inverse, PIV, peak inverse voltage for a 3-phase will be √3 Vm, √3 Vm, which will give us, so √3 times Vm, yeah, that is the expression, √3 times Vm. So those are the performance parameters for the 3-phase half-wave rectifiers, where we have 1 diode per phase. So next we can also look at now 3-phase full-wave rectifier, where we have 2 rectifying diodes per phase. 2 rectifying diodes per phase. Let us have the diagram. So that is our arrangement for the 3-phase full-wave rectifier. So you notice that we have 2 diodes per phase. So you will notice that the 2 diodes in a particular phase, they will be conducting. At the same time, when that phase voltage is more positive compared to the other 2. So this is how our waveform appears. It may look complex, but it's a simple logic here. As we know that D1 and D4 will be conducting at the same time. So when it comes to drawing, we know that our voltage V1 and our voltage V4, they will always be starting the same point and going back to 0 at the same time. So they will always be intersecting along the horizontal, but they are out of phase. Then the same, D2 and D5, the same we do for that. So you can see our V2 is also intersecting with our V5 from the other side. They intersect at that point. So I've used different colors to show the diodes conducting at a particular time or for a particular phase. So for V1 and V4, I've used black. V2 and V5, I've used red, while V3 and V6 have used the blue. So this is how our output waveform will appear. This is how we drop from the points of intersection, then we come up with our output waveform. So you can see it is almost there. If you look at it, the way it appears, the ripples seem to be less compared to the previous ones. So that is the circuit arrangement. Still, the secondary is in star, the primary is delta. So these are our voltages, V1. So now they are displaced by 60 degrees each. So V1 is Vm sine omega t, V2 will be omega t minus 60, V3 omega t minus 120 up to 300. So it is very simple to carry out the analysis. So what we need to get are the limits. So as we know, at point A here, at point A, voltage V1 and voltage V6 are equal. So I can say that at point A, point A V1 equals to V6. So we say that Vm sine omega t, Vm sine omega t is equals to Vm sine omega t at point A, we denote A, at point A minus 60 degrees. So we can get the angle omega t. So Vm, so we shall have sine omega t at point A equals to sine omega t at point A cos 60 degrees minus cos omega t at point A sine 60 degrees. So we shall have sine omega t at point A all over cos omega t at point A will be equals to minus sine 300 all over 1 minus cos 300. This gives you root 3. So therefore, this is tan inverse of root 3, that is our 60 degrees. So therefore, omega t at point A will be 60 degrees, which is pi over 3. That will be our first limit. Then we also consider point B, where now it is V1 equals to V2. So at point B, V1 equals to V2, or V1 is here, Vm sine omega t equals to Vm sine omega t. Actually, it should be omega t at B. We denote B here. Omega t at B minus 60 degrees. So Vm, so we are left with sine omega t at B equals to sine omega t at B cos 60 degrees minus cos omega t at B sine 60 degrees. So if we simplify, we shall have sine omega t at B all over cos omega t at B equals to negative 60 all over 1 minus cos 60 degrees. So you could see the lower limit we had pi over 3. But we know if we get tan inverse root 3 again, now we shall take 150. So omega t at point B, so tan inverse of that, because we know tan is positive in 2 quadrants. So the lower quadrant, the first quadrant was, that's where we had 60 pi over 3. Now in the third quadrant we shall take 300. So omega t at point B, take 300 degrees, which is equivalent to 2 pi all over 3. So these are our limits. That is a pi over 3 and 2 pi over 3. So we can see the voltage V1 will be more positive between point pi over 3 and 2 pi over 3, where it will be commutated. Then again, now V2 will be more positive now from 2 pi over 3. So that's how they will be alternating. So we can do the analysis and get maybe the VDC. So VDC will be given by 6 all over 2 pi. 6 all over 2 pi. You can see you have 6 voltages. 6 all over 2 pi. The root, the integral from pi over 3. From pi over 3 to 2 pi over 3. Then our voltage here, root 3 Vm sine omega t d omega t. So shall have 3 root 3 all over pi into negative cos omega t. That is from pi over 3 to 2 pi over 3. If you simplify these, you will get 3 root 3 Vm, 3 root 3. We have our Vm here. All over pi, which from the calculator we can have 1.65 for Vm. That is our VDC. You can get IDC. It will be VDC over RL. It is 1.654 all of Vm all over RL, which can give you 1.654 IM. VRMS VRMS, okay, the square root 6 all over 2 pi, the integral from pi over 3 to 2 pi all over 3, then we square our voltage, that is root 3 Vm sine omega t, we square that with respect to omega t. All these we get the square root. So this will be equals to 9 Vm squared all over pi the integral from pi over 3 to 2 pi over 3. So the sine squared, we write it as, that is from the SNP, 1 minus cos 2 omega t, all these over 2 omega t. So we get the square root. So all that is raised to a half. So maybe another more step. So we can have 9 Vm squared all over 2 pi into 2 pi over 3 into omega t. We integrate one with respect to omega t minus sine 2 omega t all over 2 from pi over 3 to 2 pi over 3. We get the square root. So on simplifying these, we should have 1.655 Vm as our VRMS. So IRMS, so therefore IRMS would be VRMS all over RL, which gives us 1.655 IM. Okay, this is Vm all over RL. So answer becomes 1.655 IM. That is the IRMS. Ripple factor, the same procedure. Ripple factor. It is the square root VRMS all over VDC. We square, we subtract 1, which you can have the square root 1.655 all over 1 point. The other one was 1.654. Squared minus 1, giving 3.47. 3.47%. Maybe the efficiency PDC over PAC, VDC is VDC times IDC all over PAC, which is VRMS times IRMS. So this will be 1.654 all over 1.655 squared. This gives you 99.93%. So you can see the more the faces, the better the efficiency of the rectifier here. So that one brings us to an end for today, whereby for the next lesson we shall now look at the questions touching on three-phase. Then we shall also look at, we are left with six-phase half-wave. Then we go to control rectifiers now, where we use the thyristors. So probably the next lesson we shall mark the end of our topic on rectifiers. Thank you.